Ventilation. So we've been talking about low energy buildings and what low energy buildings need. And low energy buildings need insulation. So we need to stay warm. Just keep the building warm. We need to insulate. We also need air tightness. So just insulation is not enough. We need to stop the air leaking in and out of the building. And we need good windows. We need to watch out for thermal bridges. So this means where we put the windows in the house, where the walls connect the roof. If we bang pieces of metal through the wall, that's going to mean the insulation doesn't work very well because the heat will go through what are called thermal bridges. So we need to have a house with no thermal bridges. And also, probably we've talked about good form factor. So when we start designing the house, the shape of the house, some shapes are very easy to make into low energy. The more corners and the more sides they are, the more difficult it is to make it low energy. So the form factor is also helpful. So for insulation, we've talked about we can measure insulation. We can calculate the U value, so we can work out each element that goes into a wall or into a structure. We can work out what the U value is by calculation. You can also measure U value, so you can make an experiment where you have a hot place on one side of a wall and a cold place on the other, and measure how much heat we're losing. Often Q in Japan, Q sheet, or the Q value is often used to measure insulation. So this is how much heat the building loses through the area of, well, you can measure it by the area of wall, or you can measure it against the floor area of the building. Air tightness is measured. How do you measure air tightness? We can measure most things if we try, and if we want to make a low energy building, we need to measure so we can find out how much energy we're actually using. And we can measure air tightness. In Europe, the measurement in Europe is usually air changes per hour at 50 pascals. I'll talk about that in a moment. Japan uses the C value, the shichi, and this is an idea of square centimeters per square meter. So if you imagine any wall has lots of holes in it, and if you kind of add up the area of the holes, this gives you the C value. The European measurement is what you do is put a pressure difference inside and outside the house, and then just see how long it takes for the air to leak in. So the pressure difference is usually 50 pascals, and so you see how long it will take for all the air in the building to change. And this is usually done with a blower test. So you shut all the windows, shut all the doors in the house, except one place, one window or one door. And you put a blower in there to blow the air out of the house, and then see how long it takes for the air to leak back in through the leaks as the pressure. So as you blow air out, the pressure inside drops, and then the pressure starts to rise again. So you can measure how that works. You could also do a reverse blower test, so you can blow air into the house and the pressure goes up, and then see how quickly it is before that air leaks out of the house. So we can measure this, and we do measure this for low energy buildings because air tightness is important. When you measure it, you get a graph something like this. So this is a plot of the pressure and how much air is leaking through. And from this, we can work out how many air changes per hour. And you can also calculate back to the C value from these measurements. So that's how to measure air tightness. We know how to measure air tightness, we know how to measure insulation. So what happens if a building is not airtight? If our building is leaky, if it's leaking air through the walls, then two things can happen. One of them, of course, if the air is leaking through the walls, if it's winter and your house is nice and warm inside, then any air that leaks out through the walls, you're losing heat. And if it's very cold outside and very warm inside, or nice and warm inside, then you'll lose lots of energy, and there's extra heating to make up for all the air that you're losing and all the warm air that you're losing from your house. Also, if it's not airtight, there's a risk of condensation as hot air moves through your walls and cools down. There's a risk somewhere inside the wall you can get condensation. Just a reminder of how to, if you want to get condensation, how you get it is if the walls are airtight and not insulated. So if you just have a thin wall that doesn't let air through, or a thin window, then you'll get condensation, you'll get water forming on the inside of the wall in the winter. If you have the opposite, if you have an insulated house that's not airtight and air is able to leak through the wall, then you'll get condensation inside the walls, which may be worse. If your house is not insulated and is not airtight, then you do not get condensation. Condensation is not a problem. However, it will not be very warm in the winter. So that may also not be ideal. And insulated. So what we want is insulated and airtight. And do we have any problems if a house is insulated and airtight? Well, we do need air, and this is where ventilation comes in. So if the house is airtight, we will get problems because we need air in our house. Why do you need air in the house? How much air do you need? And how can you change it? So how can you get air into your house? And in the process of changing the air, how much heat will you lose? So please think about these questions, and we'll look at them in a moment. So we need fresh air. The first thing you think about is often carbon dioxide that we need to breathe. In fact, oxygen is not a high priority for ventilation. There's plenty of oxygen in the air. Carbon dioxide is a problem. We breathe out carbon dioxide, and when carbon dioxide levels go up, it starts to get a bit sleepy. When it gets higher, we start to get headaches, and carbon dioxide levels need to be kept down. So we need ventilation not to bring in oxygen so much, but to get rid of carbon dioxide. And most ventilation we need is to get rid of things in the air, not to bring things in, but to let things out. For example, if we're cooking, especially if you use gas, but anything that you're cooking releases chemicals into the air, things start to smell. You have many materials have what are called VOCs, volatile organic compounds, formaldehydes and other chemicals. We have these in furniture, in clothes, any house, especially a new house with new furniture and new paint. There are lots of chemicals coming off, which we need ventilation to get rid of. But in this list, the number one need for ventilation is moisture. So we need to think about moisture. And these numbers are in litres per second. And the design for a house, for a home, we should try to design 8 litres per second per person. Another thing that's not on this list that you may be thinking about in 2020 is viruses and diseases. And of course, we need ventilation for viruses and diseases. This is very important in hospitals where we know people are sick and we know people have diseases. And in a hospital, you need more than this level of ventilation. If it's in your home, the recommended design ventilation is 8 litres per second per person. What does that mean in terms of the house? So if we look at the a house, that's 30 cubic meters per person per hour. We usually measure ventilation also in air changes per hour. So how many air changes per hour is this? To know this, we need to know how big the room is. And for a house, we usually think of a house with 35 square meters per person is an average amount. Some houses are smaller, some houses are bigger. The roofs may be 2.5 meters high. So the volume per person is about 87.5 cubic meters per person. So we can work this out. It comes to 0.34 air changes per hour. So this is our target. This is the amount of ventilation we need to keep our house from moisture building up and from problems with moisture. If we do this, we won't get any other problems with carbon dioxide or VOCs or other problems. Next question is, how do we get this fresh air, or how do we get rid of this old air? And there are different ways to change air. How many can you think of? I can think of 4 simple ones. One of them is opening windows, and you may also have air vents. So you could build, rather than windows, you could make holes in the wall. You can use extractor fans, so you can blow the air out of the house. Or you can use a more sophisticated ventilation system. Each of these has advantages and disadvantages, and let me just talk about the advantages and disadvantages of each of these systems. So first of all, what are the advantages? And how do they work? How do they exactly work? So what's called natural ventilation. We can get natural ventilation through a house in different ways. For example, we could have an open window on 2 different sides of the house, and we usually get a pressure difference. So as the wind is blowing, often there's high pressure on one side of the house, lower pressure on the other. If we open the windows, air will go through from high pressure to low pressure. We can have what's called a stack effect. If we open one window upstairs and another one downstairs, or this way, or whichever way you open your windows, then you can get air will blow this way and ventilate out through the house. These will work more or less, but often this will either give us too much ventilation or not enough ventilation. If we're trying to get a target amount of ventilation, if it's very still, then we may get no ventilation from opening these windows. And if it's very windy, then we may get too much ventilation. So is too much ventilation bad? Well, remember that if it's winter and it's warm inside, we have lots of nice warm air. So as we're ventilating, we're losing all of that air. So one reason ventilation is bad is in heat loss. And as a house gets more insulated, as we get better insulation and we lose less heat through the walls, the heat we lose through ventilation that becomes a bigger part of our heat loss. So if we're trying to get a low energy building, then we need to think about heat that we're losing through ventilation. And so we can work this out. If we've got 8 litres per second per person, let's say it's 20 degrees inside, it's freezing outside. We know how much heat is in the air, and we know how many litres in a cubic metre. So we can work out how many watts we are losing if we're ventilating 8 litres per second per person. How many watts are we throwing away in that hot air as the colder air is coming in? And here is this is an example of, so if we ventilate it, if it's winter, that's the extra heat we need per person to make up what we're losing with the hot air that we're throwing away. That's just looking at one time when it happens to be 0 degrees outside, 20 degrees inside. How much energy are we using over 1 year, I wonder? And to do this, we need to think about, well, we were talking about power before. At any given time, we can measure how much heat we're losing from the volume of air leaving per hour and the heat capacity of the air and the difference in temperature. So we can find at any one time if we know the temperature. For a whole year, we need to look at what's the temperature difference over a whole year. And to work this out, we have an idea that's called degree hours. So we can look at the temperature and time. And if we imagine we're keeping it 20 degrees inside, and all the time the temperature outside is changing. So sometimes there's 5 degrees difference, and sometimes there's 10 degrees difference, and sometimes there's maybe 4 degrees, and sometimes there may be 15 degrees difference. And we can, each hour, we can add up how many degree hours there are. So the first hour is a 5 degree temperature difference, then the next is 6 degrees, so that's 11, then the next is another 6, so that's 17. So we can keep adding up. And we can add these up over a year, and we get the degree hours. This is usually measured in kilokelvins hours per year. A means year. That's Latin, by the way. Kilo is 1,000. Kelvin is the temperature unit, and hours, 1 hour, 60 minutes. So we can measure this. This is kilowatt hours per year. G is kilowatt hours. That's in kilowatt hours per year. Kilokelvin hours per year is 1,000 degree hours per year. Matsumoto, for example, is about 80. To have a building in Matsumoto, heat it for a year, will take about 80 kilokelvin hours. So we can work out, using this number, we can work out how much heat do we lose in a whole year. And we do this by putting the numbers in. 1.5 is still the heat capacity of air. It's 0.008 is 8 litres per second, and it's 80,000. When we're doing these calculations, we need to be very careful of the K's. The K for kilo, the small k. The big K is Kelvin. Once we use a K, we may get 1,000 times wrong for our answer. And we want to try to get the answer in kilowatt hours. So if we calculate this, this is what we get. We get 770 kilowatt hours per year. So this is how much heating, if you want to stay warm, if you want to stay at 20 degrees for the year. This is how much heating you're going to need per person for your house to stay warm and